Welcome to the Screencast 3. In this screencast, we will construct the speciation diagram and Power diagram for the nickel ammonia citrate system. As always, we begin by constructing the speciation diagram. This means we are solving for the activities of all species at the same oxidation state, in this case nickel 2. Recall that when we introduced ammonia into the system, nickel combines with ammonia to form a series of nickel-ammonia complexes, each with different number of ammonia ligands. These are known as nickel-amine complex. Now, when we add citrate, nickel can combine with citrate to form a separate series of complex, the nickel citrate complexes. The activity of each nickel citrate species depends on the free nickel ion activity and the free citrate concentration. Just as we had an ammonia-ammonium equilibrium to account for, we now also need to consider the citrate protonation equilibria. Citrate undergoes three-step deprotonation reaction. Citrate picks up a proton to form hydrogen citrate with a pKa of 6.40. Hydrogen citrate picks up a proton to form dihydrogen citrate with pKa of 4.79. Dihydrogen citrate picks up a proton to form a citric acid with a pKa of 3.14. So the three pKa values 3.14, 4.79 and 6.40 govern how the total citrate distributes itself across its four protonation states as a function of pH. Previously, when we add only ammonia in the system, our unknowns were the free nickel activity and the free ammonium activity. Now that we have added citrate, we introduce an additional unknown, the free citrate ion activity. Once the free citrate activity is known, all the citrate species HCl2-, S2CIT- and S3CIT can be calculated directly from the thermodynamic equilibrium expression for each protonation step. As we established in Screencast 2, the activities of all species in the speciation diagram are computed from the mass balance. Previously, we had two mass balance equations, one for total nickel and one for total ammonia. Now that we are adding citrate to the system, we need a third mass balance on citrate. So the three mass balance equation we will use to construct this speciation diagram. The first is a nickel balance. The total dissolved nickel must equal to the sum of free nickel ions, all nickel amine complexes and all nickel citrate complexes. The second is the ammonia mass balance. The total ammonia added to the system must equal the sum of free ammonia, ammonium ion and all the ammonia ligands bound up to the nickel amine complexes, since each complex consumes a different number of ammonia molecules. The third is a citrate mass balance. The total citrate added must equal the sum of free citrate in all of its protonation state, Cit3-, HCl2-, S2CIT- and S3CIT, plus any citrate that is coordinated to nickel in the nickel citrate complexes. These three equations combined with the thermodynamic equilibrium expression from the previous slide give us the system we need to solve. The unknowns are the free nickel activity, the free ammonium activity, and the free citrate activity. As we established in Screencast 2, the form of Nernst equation does not change when citrate is added to the system. To understand why, consider what happens when a nickel citrate complex participates in electrochemical reaction. First, the complex must dissociate. Nickel citrate breaks apart to release free nickel ions. This dissociation step is a chemical equilibrium, not a redox reaction. Once the free nickel ions are released, the actual electron transfer, the reduction of nickel 2 plus to metallic nickel, is identical to what it would be in any other nickel system. The Nernst equation therefore takes exactly the same form as before. What does change, however, is the activity of free nickel activity. Because citrate complexes nickel strongly, a large fraction of the total dissolved nickel is tied up in nickel citrate complexes rather than existing as a free nickel ions. This means the free nickel activity is significantly lower than it would be without citrate present. And since the Nernst equation depends directly on the activity of nickel, this reduction in free nickel activity shifts the equilibrium potential. So while the equation itself is not changed, the potential it predicts will be different because the input The free nickel activity had changed as a result of complexation with citrate. This is the in-depth theoretical foundation. I will see you in Python implementation. We begin, as always, by importing our libraries. We bring in NumPy for numerical computation, Matplotlib for plotting, and least square from SciPy to solve our mass balance equations. The next step is to define our constant for the system. Let us assume that the total nickel concentration is 0.2 molars, the total ammonia concentration is 2 molar, that is 10 times the nickel concentration, and the total citrate concentration be 0.3 molar. The Ka of ammonium and the cumulative formation constant for the nickel amine complexes beta 1 through beta 6 are exactly the same values as we used before. Now we introduce something new, the thermodynamic equilibrium for citrate protonation. Citric acid undergoes 3 stepwise deprotonation reactions, so we define 3 pKa values, pKa1 as 3.14, pKa2 as 4.79, and pKa3 as 6.40. From these, we compute the corresponding Ka values. Then we define the nickel citrate formation constant. Nickel can bind to the fully deprotonated citrate ion Ci3- to the singly protonated form HCl2- and to doubly protonated form H2CIT-. Each of these gives a different complex with its own stability constant. Finally, we define our pH grid, 1000 evenly spaced points between 0 and 14. 1000 steps gives us smooth, well-resolved curves across the entire pH range. Next, we assign colors to every species we will be plotting. We pull from 3 Matplotlib color maps, tab20, tab20b, and tab20c, which together gives us enough distinct color for all our species. Tab 20 covers the free nickel and amine complexes, Tab 20b covers the citrate species, both the nickel citrate complexes and the free citrate forms, and Tab 20c handles free ammonia and ammonium. Now, we define our core speciation function. This takes the pH and the 3 free concentrations, free nickel activity, free ammonium activity, and free citrate activity, and returns every species in the system. From pH and free ammonium, we first calculated free ammonia using the Ka of ammonium. Then using the cumulative formation constant, we compute all 6 nickel amine complexes. For citrate, we wrap the calculation in an if-else block. This lets the same function handle both the ammonia-only system and the full ammonia citrate system without any changes. If free citrate is present, we calculate all the protonated citrate forms, HCl2-, H2CIT-, and H3CIT by working up the protonation ladder from Cit 3-. We then compute the 3 nickel citrate complexes from the free nickel and the corresponding citrate form. If citrate is absent, everything is simply set to 0. Finally, the function sums up the 3 mass balance total nickel, total ammonia, and total citrate, and returns them alongside every individual species concentration. Now we define the solve pH function. This is the heart of the entire calculation. Given a single pH value and 3 system totals, total nickel, total ammonia, and total citrate, it returns the concentration of every species at that pH. The function works through 4 steps. We start with the quick preliminary calculation. From the pH, we compute the hydroxide concentration using Kw, and from the hydroxide concentration, we compute the saturation concentration of nickel, the maximum free nickel the solution can hold before precipitation begins. We also check which ligands are actually present using the simple flags like HADS, NHADS, and HADS citrate. These flags are what drive if-else branching throughout the rest of the function. Step 1 is to find the free concentration of nickel, ammonium, and citrate that satisfy all 3 mass balance equations simultaneously. We cannot solve this analytically because the equations are coupled and nonlinear, so we use least square from SciPy to solve numerically. We define a residual function called mass balance error that takes a guess for the free concentration, calls species from free to compute what total would be, and returns the difference between those computed total and the actual total. The solver iterates until that difference is driven to 0. Notice that scaling array normalizes each residual by that corresponding total concentration. This keeps all 3 equations on the same numerical scale and helps the solver converge reliably. The if-else structure here mirrors what we saw in species from free. If both ammonia and citrate are present, we solve a full 3-variable problem. If only ammonia is present, we solve for 2 unknowns and set citrate to 0. If only citrate is present,
experiment, we solve for nickel and citrate with ammonia set to 0. And if neither of the ligand is present, it reduces to finding just the free nickel activity. The initial guess, X0, is carried out in the form of previous pH step. This warm starting strategy is important because it keeps the solver close to the solution and it prevents from wandering into unphysical regions. Step 2 is to check whether precipitation occurs. We take the free nickel ion concentration found in step 1 and compute its ionic product with hydroxide. If that ionic product is at or below Ksp, the solution is undersaturated. No solid forms in this case. The free concentration from step 1 are physically valid and we call species from free function one final time to expand them into individual species and return it at that time. Step 3 handles the case where precipitation does occur, meaning the ion product exceeds Ksp. In this regime, the free nickel ion concentration cannot be as high as step 1 suggested because the solid is actively removing nickel from solution. So we pin the free nickel ion concentration at its saturation value and resolve only for the ligand concentration under this new constraint. The structure is again branched on which ligands are present. This second solve ensures that the ammonia and citrate mass balance are still satisfied even after nickel has forced down to its saturation level. Step 4 is a final mass balance on the solid phase. All the nickel that remain dissolved must be precipitated as nickel hydroxide. So the solid concentration is simply the difference between the total nickel and total dissolved nickel written by species from free function. We use max with 0 to avoid any small negative values from numerical rounding. Finally, the function returns every species concentration: dissolved nickel, solid nickel hydroxide, free ammonia and ammonium, all 6 complexes, all 3 citrate complexes, all 4 citrate forms, along with the free concentration vector. That vector is what gets passed as a warm start guess to the next pH step, ensuring that the solver state converts cleanly all the way across the 1000-point pH grid. Now, we define the single sweep function. It walks through every pH point in the grid, calls solve pH at each one, and collects all the result into set of arrays that we can plot. We start by defining list of species keys and creating an empty array for each one, initialized to 0. We also create a norms array of the same length which will track the residual error at each pH point, which is useful for checking that the solver converts properly everywhere. Then we enter the main loop. At each pH step, we call solve pH and unpack all the species concentration it returns. We also get back the updated free concentration vector x0, which immediately becomes the warm start guess for the next iteration. This is the chain that carries convergence from one pH step to the next across the entire grid. After each solve, we do a quick verification. We call species from free with the free concentration just found and check how well the mass balance are actually satisfied. The residual norm at the pH point is sorted in the norms array. If the solver converts cleanly, these norms should be very small, close to 0, across the whole pH range. If we see large value at any point, it is a signal that the solvers struggle there and the result may need a closer look. Finally, all species concentration are stored into their respective arrays, one entry per pH point. The function returns the full dictionary of arrays and the norms array together. Everything we build to the speciation is now in one place, ready to be plotted. Now, we wrap everything into a top-level speciation function. This is the function we will actually call to produce the result. It starts by setting up the initial guess, half the total concentration for each species that is present, and 0 for any that are absent. Then comes the key idea of the function. Rather than sweeping through the pH grid just once, we run the sweep twice. Once forward from low pH to high pH and one backward from high pH to low pH. Each sweep produces its own set of species arrays and its own set of residual norms. After the backward sweep, we reverse its array so that both sweeps are aligned in the same direction before we compare them. Then for every species at every pH point, we pick whichever sweep give the lower residual norm at that pH point. This is the best of the two strategies. If the forward sweep converged well at a particular pH, we will use that result. If the backward sweep converts better, we use that instead. The NP that were called handles this selection cleanly across the entire grid in one line. The reason we need this is that the solver can sometimes get stuck in poor local minimum when approaching a difficult pH region from one direction, but converges cleanly when approaching from other direction. Running both strips and taking the better result gives us the most reliable solution across the full range. The function returns a single dictionary of arrays, one per species, covering all 1000 pH points ready to plot. Now, let's write the Pobe function. This function is identical to one we wrote for the pure nickel and nickel ammonia system. It takes the pH and the free nickel activity and returns 8 equilibrium potential line. R1 through R6 are the Nernst equation for the 6 redox boundaries in the nickel system. The transition between nickel 2 plus, nickel hydroxide, nickel oxyhydroxide, and nickel dioxide, OER and HER are the oxygen and hydrogen evolution line that define the stability window of water. None of these equations have changed. The electrochemistry is the same regardless of whether citrate is in the system or not. Now is the time to actually call the function we have built. We call speciation with our PS grid and it runs full forward and backward sweep, solves the mass balance at all 1000 PS point and returns the results as a dictionary. We then unpack that dictionary into individual named arrays, one for each species, so they are easy to work with when plotting. With the free nickel activity array in hand, we immediately pass it to the Powe function alongside the PS grid. This gives us all 8 potential boundaries for the Powe diagram. Everything is now computed. The next step is to plot it. Now that we have defined all the functions and computed the speciation result, we can plot them. Let's walk through the plotting code. We start by building an automatic title that checks which ligands are present and appends them to the system level, including the ligand to nickel ratios. We then create the figure an empty list called handles nickel to collect all the lines for the legend. The first block plots the two core nickel species, free nickel and solid nickel hydroxide, with solid lines and slightly heavier weight. If ammonia is present, all 6 nickel complexes are added with solid lines. If citrate is present, the nickel citrate complexes are drawn with dashed dot lines and the free citrate forms with dotted lines. This is visual separation, makes it easy to distinguish bound from free citrate at a glance. Vertical lines at the 3 citrate pKa values are also added with the small text annotation. Running this all species at once, the plot is it seems to be too cluttered to read clearly, so let's verify the equilibria one group at a time. First, we set ammonia concentration to 0 and plot only the nickel and the citrate species. Crossovers fall exactly at PS 3.14, 4.79, and 6.40, precisely at the pKa values. The citrate speciation is correct. Next, we switch ammonia back to 2 molar and replot. On the right axis, the ammonia and ammonium crossover falls exactly at pH 9.238. The ammonia equilibrium is also confirmed. You may also notice a discontinuity in the curves at higher pH. As we covered in the previous screencast, this is where the solver switches from the unsaturated regime to the precipitation regime. Free nickel ion gets pinned at its saturation level value and the ligands are resolved, introducing a small numerical jump. Drawing a vertical line at the pH where nickel hydroxide first appears confirms that this is exactly at pH 10.92. With all equilibria verified and the discontinuity explained, we are ready to construct the Powe diagram. With the speciation diagram completed, we now plot all 6 electrochemical boundary lines for the nickel system. Each line defines an equilibrium between 2 nickel species as a function of pH and potential. R1 and R2 bound the stability of nickel metal. R3 through R6 maps the transition between the oxidized species. Nickel 2 plus, nickel hydroxide, nickel oxyhydroxide, and nickel dioxide. The dashed OER and HER lines are included as reference, marking the thermodynamic stability window of water. This step is similar to what we did in the previous screencast for nickel only and nickel ammonia system. We plot all the electrochemical boundary lines across the pH and the potential window. However, you will notice the lines are slightly shifted or curved compared to before, reflecting the influence of additional species in the system. Here in this function, we stack all nickel species, including the free ion, nickel hydroxide, nickel ammonia complexes, and the citrate complexes, like nickel citrate, nickel hydrocitrate, nickel 2 citrate, and at each pH point, we identify which species has the highest concentration. That dominant species index is then used to assign a domain flag to each region. We then split the domain into two broad categories, dissolved and solid. Dissolved covers nickel 2 plus and all the complexed forms, while solid corresponds to nickel hydroxide. The distinction matters because it controls which electrochemical boundary lines apply at each pH. For dissolved dominated regions, R1 sets the lower stability limit and R3 the upper. Where nickel hydroxide dominates, we switch to R2 and R4 instead. A NP that were call handles the switching cleanly across the full pH grid. Finally, R5 is set as a second upper boundary representing the nickel dioxide nickel oxyhydroxide transition, which sits above R3 and R4 across the entire range. Now, we plot only the relevant boundary lines for each pH rather than all lines simultaneously. As previously stated, R1 and R3 are drawn only where dissolved species dominate, while R2 and R4 appear only where nickel hydroxide is the dominant solid space. The result is a much cleaner diagram. Each boundary line only appears where it is physically meaningful. Now, we write a final function for creating a final Power diagram, bringing everything together into a single colored stability map. The diagram is built in two layers. First, the broad electrochemical regions, nickel metal at the bottom and nickel oxyhydroxide in the middle, oxidizing band, and nickel dioxide at the top are filled using the lower and upper boundary lines we defined previously. Then within the stability window between E lower and E upper, we fill each dissolved or solid domain with its own color marks to only appear where that species dominate. Importantly, the code handles the system composition conditionally. Ammonia complexes are only added if ammonia is present and citrate complexes only if citrate is present. This makes the diagram flexible across different system configurations. Finally, the boundary lines and these water stability lines are overlaid to complete the diagram. And this brings us to the end of Screencast 3. Thank you for watching.